Good afternoon. My name is Renelle Miles, and I want to welcome you to the NIH Office of Disease Prevention's Medicine Mind the Gap series. This seminar series explores issues at the intersection of research, evidence, and clinical practice, areas in which conventional wisdom may be contradicted by recent evidence. From the role of advocacy organizations in medical research and policy to the importance of behavioral interventions, the Office of Disease Prevention hopes to engage the prevention research community in thought-provoking discussions to challenge what we think we know and to think critically about our role in today's research environment. Before we begin, I have some housekeeping items. To participate by Twitter, follow us at NIH Prevents and submit questions using the hashtag NIHMTG. You may also email questions to prevention@mail.nih.gov. There is also a link to a feedback form at the bottom of the videocast page where you can submit questions during the talk. At the conclusion of today's talk, we will open the floor to questions that have been submitted via email and Twitter. Lastly, please visit the seminar page on the ODP website, prevention.nih.gov/mindthegap, following today's talk, and click the link to the seminar evaluation under the resources section to submit your feedback about this seminar. At this time, I'd like to turn things over to Dr. David M. Murray, Associate Director for Prevention and Director of the Office of Disease Prevention.
Thanks, Renelle. It's my pleasure to introduce our speaker today. Dr. Stephanie Lanza is a professor of biobehavioral health and the scientific director of the Methodology Group, the Methodology Center at Penn State. She has a background in research methods, human development, and substance use and comorbid behaviors, with papers appearing in both methodological and applied journals. She's co-author of the book Latent Class and Latent Transition Analysis, published by Wiley in 2010, and led the development of PROC-LCA, a SAS procedure for fitting latent class models. Her research interests include advances in finite mixture modeling and time-varying effect modeling to address innovative research questions in public health. She's passionate about disseminating these methods to help health, behavioral, and social science researchers, and has organized many NIH-funded dissemination conferences, taught many hands-on workshops, and written tutorial articles to enable applied researchers to use the latest methods based on her work. At this time, I'd like to welcome Dr. Lanza and turn the session over to her at Penn State.
Hi, thank you very much, David. Thank you, Renelle. I'm very pleased to be here today. So the title of this Mind the Gap talk is Time-Varying Effect Modeling to Study Developmental and Dynamic Processes. And so I'll be referring to Time-Varying Effect Modeling as TVM for short in this talk. The talk is structured as follows. I'd like to give a little bit of a background, a history of the method, if you will, and then present two empirical studies in brief. The first study is one focused on nicotine addiction and the recovery process, and we'll focus on recovery as a dynamic process. The second study is going to be focused on the onset of e-cigarette use in adolescents in the U.S., and this study will take on a more of a developmental perspective. And I'll just conclude with a few final thoughts. Okay, so into the background. I would argue, as many would, that human behavior as it relates to health is dynamic. And this orientation is highly relevant for understanding a lot about health behavior. So, for example, we can think about behavioral changes. Behavior is dynamic, so it may change across age, developmentally. It may change across time in real time. There may be changes in processes related to the behavior. So, and again, the change in those processes may be across developmental age or real time. And also we can think very creatively about dynamic or differential intervention effects. And so behavioral interventions might have effects that develop or evolve or wash out over age or real time. And so one motivating example for why we're here today is to think about negative affect and craving. So negative affect and craving to smoke cigarettes among addicted smokers. Those are tightly linked in addicted smokers. Excuse me, and when they quit smoking, what does recovery look like? TVM can address questions that we don't typically pose or address with our standard methods. For example, is negative affect differentially associated with craving for nicotine at various points throughout the smoking cessation process? Or how does a smoking cessation intervention affect that link between negative affect and craving over time? And so you can get a sense of the essence of time or dynamics in these research questions. So first, let's do a thought exercise together. So let's suppose that an alcohol abuse behavioral intervention was administered, and there was a two-arm trial. So you had the control group and the treatment group that received the intervention. And after the treatment was implemented, or the intervention was implemented, perhaps you had one time point assessed post-baseline measurement of heavy drinking. Or another way to design the study would be to assess post-treatment, say 2 time points of measurement. Or you could get a little bit more intensive on the data collection post-treatment and get multiple or even many time points post-intervention. And you might think about the intervention effect showing itself or manifesting itself in sort of like a moving window of time. And so you would need a lot of time points to see that. And so if we had only one time point post-treatment, we might see that the rate of heavy episodic drinking after the intervention was, say, around 0.46 for the placebo group and 0.25 for the intervention group. And if that is found to be a statistically significant difference, we can say that our intervention worked and we're done. But perhaps we also have a second post-treatment assessment time point. And so in this case, we have the same time 1 data, but now we also have the individuals followed to time 2. And we see that the rate of heavy episodic drinking remains fairly steady in the placebo or control group. But we see that at time 2, the intervention effect may be weakening. That is, that the intervention group is starting to increase in their rate of heavy episodic drinking. And so you can see a time varying effect of this intervention. Now, suppose we actually followed individuals 10 time points. And so now we have the same data from times 1 and 2, and we see this early weakening of the effect. And that weakening kind of continues, but maybe after some developmental period or after some event around time 8, we see a resurgence of that intervention effect, for example. And this is an example of a time varying effect that we would not be able to observe with a single time point post measurement. Okay, so that's just to get us thinking about this idea of time varying treatment effects. So what is TVM? What are we here to talk about? The time varying effect model is actually a very elegant and straightforward extension of the linear regression model that we all know. And the development of TVM originally was funded by NIDA through a P50 mechanism that was awarded to the Methodology Center at Penn State. And so Renzi Lee, my colleague here in the Methodology Center, was the statistician who brought this to life. And so why do we collect longitudinal data as behavioral researchers? Well, we typically want to capture temporal change in some outcome over time. And often we want to capture time varying covariates, things like contextual variables that might be changing with time at the same time point as the outcomes. But wouldn't it also be natural to expect that the associations between covariates and outcomes may be changing with time? And TVM is designed to evaluate whether and how those associations might change with time. Okay, so let's get a little bit more concrete. Again, TVM is a direct extension of the regression model. So what is regression? Regression coefficients express associations between variables, between an X and a Y, say. And so the traditional linear regression model for predicting an outcome Y from a covariate X looks like this. So we have Y equals beta naught plus beta 1X plus an error term. And it's that beta 1 is of interest. Usually we're looking at the effect of X on Y, and that's characterized in the beta 1. And the beta 0 is our intercept or our mean value on the outcome for a certain value of X. Okay, so we interpret those beta naught and beta 1, the intercept and the slope. Now TVM modifies the equation as follows. It allows any coefficients in your equation, the intercept, the slope, or both, to be dynamic. And so that's denoted in the statistical model with a parenthetical T for time And time can take on a broad set of meaning, but we're going to refer to it as time for now. So you'll see that the intercept function is a function of time and the slope is a function of time. And so that allows us to estimate regression coefficients as a flexible, non-parametric function of continuous time. And so we can have these parametric functions for our slope coefficient, for our intercept coefficient, and so on. And the results are too large to present in tables typically, and so we always look at these regression coefficients as functions that are plotted in a figure. And so we would interpret this coefficient function, for example. And so as you see with the blue line on the chart, we see that the regression coefficient around times 1 through 3 is negative, and then there's a positive regression coefficient between times 4 and 15, and then it basically goes to 0. Or I'm sorry, this is hovering around 0, and it says minus 0.2 on the plot. And so you get a sense of how regression coefficients, betas, can vary with time on the x-axis. Okay, so just a little brief history of TVM. I think it's interesting because the history is so brief. It's nice to take stock of where we're at. So in the 1990s, theoretical statisticians did work on functional regression analysis, was introduced in the statistical literature, and some of those papers had an impact in the field of statistics, but that impact did not cross over to the health and behavioral science as it could have. So it wasn't until 2010 when, led by Dr. Runzi Lee at Penn State, the TVM software and procedure was developed as we know it today. In 2010, Dr. Lee was able to adopt these methods for behavioral scientists and work with us to address issues that we face in real data analysis. And also the software at that time was implemented as a SAS Macro that could be downloaded from the Methodology Center website. And then in 2012, we started publishing demonstration papers and doing pre-conference workshops, and we got our first R01 to apply TVM to reanalyze existing data. In this case, smoking cessation dynamics, which I'll talk about in study 1. In 2013, we did additional papers and workshops to disseminate the method, and then NIH funded a supplemental issue of nicotine and tobacco research, which came out in 2014. That was totally focused on EMA methods, and TVM was highlighted in there. And that's when we first started to see other researchers outside of the Methodology Center adopt TVM. And then last summer, we did our annual Summer Institute on this topic, and we saw a really nice pickup of researchers across the country being able to use TVM in their work quite readily. And we have been working on some software developments. And so this is the state of the art of TVM and the history of TVM. So let's get into study 1. So this is a nicotine addiction study. Again, thinking that recovery from nicotine addiction is not something that is black and white. It doesn't happen overnight. It's dynamic, right? And so we know that tobacco use is a leading cause of preventable death globally. Cessation attempts almost universally end in relapse, and withdrawal symptoms are reported as a primary reason. And so we'd like through this study to improve our understanding of withdrawal symptoms and how different smoking cessation treatments might alleviate them, in hopes that these results might inform future tailoring of interventions or different designs for interventions. And so the overall goal of this R01 was to apply innovative methods, in this case TVM and also latent class analysis, to existing data from a randomized trial to understand and inform the next generation of smoking interventions. Okay, this study was using data from the Wisconsin Smokers Health Study that was funded by NCI and awarded to Mike Fiore and Tim Baker and Megan Piper at Wisconsin. And so they did a large-scale randomized control trial. And for the purposes of this talk, we're going to think about our placebo group and all of the 5 treatment groups combined, and we'll just call that the treatment group. And real-time assessments were overlaid on this study design. Immediately post-quitting, they were assessing very intensively withdrawal symptoms, mood, behavior, and so on. And so the study design looks something like this. You can see that there was a long-term longitudinal prospective study, And between 2 weeks prior to and 2 weeks post-quit date, EMA data, ecological momentary assessments, were collected on a mobile device, and they were assessed 4 times per day for 4 weeks. And so the goal of this particular analysis is to study the underlying dynamics of craving during the smoking cessation attempt and to estimate the time-varying effect of the intervention on craving, but also, importantly, on decoupling craving from some of its key drivers, for example, negative affect. Okay, and this was published in that special issue I mentioned. So the variables in the study are craving, that's our outcome, that was assessed 4 times per day. We're going to look at the first 2 weeks post-quit. The predictors were baseline nicotine dependence, which is not a time-varying variable, but you will see in a moment that the effect of a baseline characteristic can actually unfold with time. And negative affect, which was assessed intensively. And then we had intervention group as our moderator. Okay, so first you have to specify your TVM model. And the big decision points there are thinking about, in this case within each intervention group, what varies with time. So, of course, we're expecting our mean outcome, our craving value, to vary with time. So that means that our intercept will be time varying. We also know that the observed negative affect varies with time. That's a time varying covariate. We also would like to specify that the effect of negative affect on craving may vary with time. And also the effect of baseline dependence, which is a time fixed variable, that the effect may vary with time. And in fact, we see that this is the case. Here's the statistical model that was specified in this case. So craving is a function of a time-varying intercept plus a time-varying effect of negative affect plus a time-varying effect of dependence plus an error term. And here's one of the results. So the effect of negative affect on craving, so we see the red line denotes the placebo group and the blue line the treatment group. And we see in the first 2 days after quitting smoking, these are addicted adult smokers. In the first 2 days, we see that the treatment condition, the nicotine replacement therapy and other treatments are effectively decoupling this link between negative affect and craving. So when you get into a bad mood, are you craving a cigarette in that moment? And we're seeing that the treatments are effectively reducing that link. Similarly, but with a very different result, we saw a time-varying effect of baseline dependence. And what we see is that in the second week after these adults quit smoking, during that second week, the treatment group is, their baseline dependence is less important. But for the placebo group, those individuals who were highly dependent at baseline, they're experiencing significantly more cravings during that second week. Okay, so what are the implications we could draw from this study? One important implication that I like to draw is this idea that we can think differently about intervention effects. So the interventions, not only the effect can change over time, but interventions can change the associations between variables. In this case, between baseline dependence and craving. Intervention can also, in this case, it diffused the role of negative affect, which, as we know, is a key driver of craving, which leads to relapse. And so if a treatment can break that link between mood and craving, then that might be a good way to think about how we can augment treatment in the future. And so broader implications, again, we can think about static baseline variables or individual characteristics that can have effects that change over time. And I think that this is highly relevant when we think about genetic variables that have effects that might change over time. The effects of treatments in standardized randomized controlled trials may be static. They may turn on or off, but more likely there are interventions that unfold, their effect unfolds with time, maybe in a more cumulative way, or maybe it washes out, but we don't know unless we look for time-varying effects. And so we can model intervention processes that we might suppose exist. And at the end of the day, hopefully, the kind of information we can get from studying dynamics of behavior using TVM can inform the tailoring of treatments to individuals, and importantly, I think, to time. And so thinking about the relevance of the timing of an intervention for adaptive intervention trial designs. Okay, I'm going to switch now to a totally different study and a totally different application of TVM. So this study is on e-cigarette use in adolescents in the US. And so we're going to take a developmental perspective here. And this is an early result from a new grant that NIDA awarded us to apply TVM to existing data to study substance use and abuse and co-use and comorbidities and so on. And so we're just starting to kind of unpack this large area of research. Okay, so the first this study that I'd like to show you is still under development, but we're very interested in the new phenomenon of e-cigarette use among adolescents. And so the history of e-cigarettes, as many of you probably know better than me, they were developed as a reduced harm product. And so there's a perception that they're considered a safe alternative to traditional cigarettes. And in some ways that is indeed true. So these e-cigarettes or electronic cigarettes are inhalation activated devices. And so when you inhale, there's a heat that is produced that turns on a solution that has nicotine and other additives. And so the good thing about e-cigarettes is it eliminates this combustion, but the long-term effects are inconclusive, and some negative effects have been starting to come out in the literature. But we do know that the rate of adolescent use is rising very rapidly, and perhaps it is because of the lack of FDA regulations, but it's certainly concerning because of the lack of FDA regulations today. And there is some evidence that's building that e-cigarettes may be a gateway to other tobacco products, including combustible cigarettes. Okay, so this study is going to be examining data cross-sectionally, data from the National Youth Tobacco Study. And so I know I just switched gears tremendously, going from intensive longitudinal data and EMA data to now I'm just looking at cross-sectional data, and that is right. TVM has a broad applicability in behavioral research. And so the NYTS study was funded by the CDC to, this is the most recent data that was released is from 2014. And it was a large national study to look at tobacco-related beliefs, attitudes, behaviors, also looking at exposure to campaigns around tobacco use. And the study was a large 22,007 U.S. middle and high school students. And so we retained everyone that was between ages 11 and older in this sample. And so on average, they were about 14 and a half years old. And the data were, as I said, nationally representative. And so the goal of this study, this first study, is to examine the etiology of both traditional and e-cigarette use. First, we wanted to estimate the disparities in the rates of use across adolescents throughout ages 11 to 19. And we wanted to look at disparities across sex and race ethnicity population subgroups. And so you'll see that moderation is a theme that comes up a lot in our TVM analyses. It's very straightforward to examine differential effects across subgroups. And in this case, we're talking about differential time-varying effects across subgroups. And a second goal was to estimate the rate of use of traditional cigarettes, e-cigarettes, and both products, individual adolescents who are using both of those products as a continuous function of age. Okay, so the measures in this study were that the outcome, well, a predictor was current traditional cigarette smoking, and it was coded 1 if they used recently in the past month or not, current traditional cigarette smoking, and in the entire sample of adolescents, 6.5% said yes, and also current e-cigarette smoking, which was our primary outcome. And so past 30-day e-cigarette use was actually reported in 9.2% of adolescents. A third variable we analyzed was age, and this is the important time variable in our TVM model, and you'll see age is plotted on the x-axis in the same way that real time was in the previous study. And then we have indicators of sex and race ethnicity as moderators. Okay, so again, we're at the point where we have our variables, we have our study, we have our research questions, but it's the point that is the most fun for me, I think, is when you're specifying the exact model that you want to fit. And so thinking again about what varies with time, or in this case, what varies with age. The probability of cigarette use surely varies with age, we know this. The probability of e-cigarette use varies with age. And the effects of sex and race ethnicity may vary with age, and I would refer to that as age-varying health disparities, potentially. And importantly, too, the effect of cigarette use on e-cigarette use may vary with age. In other words, the odds ratio linking traditional cigarette use and electronic cigarette use may vary with age, and that was a purely exploratory question, and we did not know the answer to. Okay, so the model would look something like this. It's the log odds of cigarette use is expressed as a function of a age-varying intercept plus an age-varying slope for sex. This would allow us to look at the sex differences and the age-varying rates of cigarette use. And similarly, this would be the age-varying effect that beta-1 indicates the age-varying link between traditional cigarette use and e-cigarette use. And so we're going to convert that to odds ratios and get age-varying odds ratios. Okay, so here's some of the results. This is in the left panel, the estimated rate of e-cigarette use for males and females as a function of continuous age. And on the right is the rate of past 30-day traditional cigarette use for males and females as a non-parametric continuous function of age. And so we see some considerable gender differences, but they don't emerge until around age 14 for e-cigarettes and 15 for traditional cigarettes, with males using higher in that mid-adolescent period. And by around age 18, we see no gender differences in use. One of the very interesting findings that we discovered is related to race ethnicity differences in e-cigarette use. And you'll see on the left panel, the rate of Hispanic e-cigarette use is significantly higher than blacks and even than whites between ages 12 and 14. And so this was a somewhat unexpected finding of early Hispanic adoption of e-cigarette use. And on the right panel, we see a less pronounced difference for Hispanic youth. And in middle adolescence, we see this expected difference of Hispanic falling somewhere in between the rate of white youth and black youth. In e-cigarettes, that's definitely not what we see, though. And finally, we wanted to look at the co-use of e-cigarette use and combustible cigarettes, traditional cigarettes. Again, thinking of e-cigarettes as a potential gateway for use of more risky or harmful tobacco products. And we see very, very significant associations, particularly in early adolescence. And so, for example, these are odds ratios on the y-axis and age on the x-axis from 11 to 19. And so we can pull out a point on this curve and interpret it. For example, among those age 12, adolescents using e-cigarettes are more than 40 times as likely to use traditional cigarettes compared to those not using e-cigarettes. And so we see incredibly large odds ratios, which drop to around 15 by high school. So what are some implications from this particular study? This approach enabled identification of key ages of risk, and that can inform perhaps targeted or age-appropriate intervention strategies. We see clearly that traditional and e-cigarette use do go hand in hand, particularly in very early adolescence. And we see that early use of e-cigarettes is significantly more likely among Hispanic youth, suggesting greater risk for future nicotine dependence in this population subgroup. So I'd like to just make a couple of concluding notes. Next steps are, it's a brave new world of big data out there, and the next steps are, I think, uncharted at this time, but there is absolutely new information contained in a lot of new contemporary data sources. It's a very exciting time for methodologists in behavioral research. Intensive longitudinal data such as EMA data or data from streaming from wearable devices. We're just on the cusp of understanding how to make use of some of that data to really inform prevention efforts. Electronic medical records, genetic data, these are other big sources of data that we need to figure out how to use. And I think big and complex data really do mean big opportunity for prevention and health. The movement toward adaptive interventions and precision medicine is going to be very exciting in the coming years. I do believe TVM has a role to play in this new age of new types of complex data. TVM can unlock new scientific knowledge from existing data. And I think it's a wonderful way to re-examine all of the wonderful NIH-funded data we've collected over the years. TVM can help elucidate complex processes that unfold with time, dynamic effects of interventions, developmental associations. For example, what are risk factors for substance use at age 12 might be different than what are the risk factors at age 16. Associations across historical time. For example, marijuana use and attitudes, that link may be shifting with historical time. And the complex link between ages of onset and later outcomes can be examined using TVM. I would just like to first acknowledge my key collaborators in TVM. So these are all colleagues here at the Methodology Center: John Ziak, Renzi Lee, Mike Russell, and Sarah Vasilenko. We work closely together on the development and application of TVM, and it's been really great fun over the last few years. And we're very, very grateful to both NIDA and NCI for funding much of this research. So again, thank you for your time.
Thank you very much, Stephanie. That was very interesting. I was struck by several things in your presentation. It's not often that in behavioral science we see odds ratios up in the 40s. I was staring at the axis, making sure there wasn't a decimal point somewhere that I was missing, but it really was 40. That's quite remarkable. And it was very interesting to hear about this new method. We have a bunch of questions that have been coming in that we want to pose for you, and Renelle and I will share that duty. Renelle, did you want to start?
So the first question is, have you found a minimum number of time points for applying TVM in a randomized controlled trial of a behavioral intervention or when assessing relationships using large longitudinal surveillance data sets?
And so, Renelle, the question was the number of data time points?
Yes.
Was the question? Yeah, so that's a great question. I wanted to have a chance to comment about that briefly. So as with so many things in statistics, in behavioral research, the answer is really it depends, and depends on so many things. Let's take a minute and just talk about data requirements for TVM more generally. If you are assessing intensive longitudinal data, perhaps with EMA or wearable devices or step counters, then individuals will have intensive data, often sporadic data, and the TVM can easily handle data from different subjects coming in at different rates, at different time points, and so on. And at the end of the day, all of the data have to be mapped onto the metric of time, a common metric of time. And so what you want to have in these highly intensive data studies is you want to have very good coverage of your time axis, and that's going to enable us to detect some of the nuances in changes or reactivity as a function of time. If you have a panel study, for example, like AdHealth, many of us are familiar with AdHealth. It has 4 waves of data collection. that began in the 90s and is ongoing today and into wave 5. And so in this case, there was a very large core sample. And if you take all person time points that were observed across the 4 waves, we had over 34,000 of them. And if you, instead of thinking about the 4 waves of the panel study, time 1, time 2, time 3, time 4, wave 1, 2, 3, 4, if you instead pull out information about what age an individual is at that assessment, exactly what age were they, and I believe with AdHealth we can code it to the nearest month, then we have coverage across age that looks like this with 4 waves of panel data. And so that allows us to very flexibly estimate functions across continuous age, developmental changes. And so the question that was posed is important, but one of the things when when we were designing panel studies years ago, 2 decades ago and further, the idea was there's this assumption that everyone had to be assessed at the same time points going forward. And if you have an intervention, then you would do your follow-ups at baseline at 3 months, at 6 months, and so on. But with TVM, it's actually a strength when you do not adhere to that. And so if you have some individuals were assessed at 3, 6, and 9 months, and others were assessed at 4, 8, and 12 months. And then if you put it all together, the information you're getting and the inferences that you're making about the population or the effects of the intervention can be quite nuanced with relatively few waves of data. And so it very much depends on the design of the study and the research question at hand. In general, it's safe to say that the better coverage you have of your time or your age axis, the more dynamic fluctuations you'll be able to detect.
Thank you. We have another question. How does TVM deal with missing values?
It's a good question. This is on the list of areas for future research, for sure. So TVM is unlike growth curve modeling, where all available data for one individual are used to get the best guess at their growth trajectory. With TVM, all available data from all times or ages are used, but it's not a within-person approach. It's a between subjects approach. And so whatever data you have at a particular point on the x-axis, a time point, those are what your regression estimates will reflect. And so if you have differential attrition, you will have potentially biased results as you go on. So, different things have been done. So, for example, in the AdHealth study, if listeners are familiar with that, you could select the longitudinal sample, people who were there at all of the ways, and eventually you'll be able to apply those longitudinal weights in TVM in the not too distant future. And so then in that case, you could use the full sample to get nationally representative data across the entire span. But for now, the best thing to do is to be very thoughtful about your missing data, to study it, to understand it, and see at what point things start to fall apart. In a 2012 paper in Prevention Science that was written by Maria Chico, a former postdoc of the center, we actually include relapse to smoking was one of our primary outcomes. And we were looking at individuals during a cessation attempt. And so some individuals quit relatively quickly, and some relapsed very, very quickly, and others did not. And so we looked at time varying differences early on in the process of recovery, and we separated them in a multi-group TVM by those who relapsed early and those who did not. And it was remarkable how you could see quite different processes in those first few days after quitting for those who did and did not relapse. And so, of course, the ones who did relapse, they all attrited early. And so for that reason, we did not want to estimate the population level rates of craving over the full window of time, for example. And so we reduced the window of time, and we actually differed it by those who did and did not make it through the study. And it ended up being very interesting.
Okay, thank you. Another question is, your presentation covered several interesting issues regarding the role of baseline variables in outcomes, potentially time varying. A challenging problem, it seems, is what implications are there for longitudinal modeling when treatment and control groups differ at baseline, as was the case in one of your first slides. Controlling for baseline could potentially introduce more problems than it solves. What is your perspective on this?
Okay, this is a complex issue, and it's a kind of nuanced. I probably won't cover all of it now, but the first study that was a randomized controlled trial of smoking cessation treatments and its effect on relapse and craving and dynamic processes, that was truly randomized at baseline. And so baseline nicotine dependence in that study was equivalent in the placebo and the control groups. And then individuals were randomized to treatment, and then we looked at how within a treatment condition, how that baseline dependence eventually related to their craving throughout that 2-week window of recovery. And so I don't see any issues with that in this case because, again, they were randomized at baseline. I'm not sure. I think there's something more to this question, but I'm not quite sure what it is.
And the person who asked the question may, upon looking at that early slide that you showed, may have thought, well, there's a difference at baseline between the two arms, but that's not actually what you were showing in the graph. You were showing an effect of the baseline level on an outcome and how that varied over time.
That's correct. So the randomization worked very well in that study, and the individuals in the placebo and the treatment groups were essentially the same.
Right.
But the effect of baseline dependence was different for those who received treatment than those who did not receive treatment. And so it's a very complicated story of the role of baseline dependence in this treatment process because it's moderated by treatment group and it's moderated by time.
Okay, thank you. If most of the people watching this and most of the people who will watch it going forward, because it'll be recorded and available on our website, are going to be new to this method. They won't have experience with it. What advice would you give to somebody who wants to get acquainted with it, wants to get started? Are there classes, are there readings, are there other kinds of things? I know the Methodology Center has that available. I don't know if there are others around the country that do. What advice would you give to someone who's just starting to play with this or to think about it?
So I'm as you are aware, I'm very passionate about the training opportunities. They are not as frequent as I would hope, and so far they're only what's available through the Methodology Center. I will go to this one slide. So TVM is a SAS Macro, as I said earlier. And it's because it was supported by funding from NIH, it's free for anyone to download from our website at methodology.psu.edu. And there's a corresponding user's guide that I would highly recommend that you download at the same time. And the user's guide has very technical information about how the estimation is done and information about model selection and so on. But it also has the how-to kind of information. It has the information about basics, about syntax, and how you specify the different parameters in the macro. And so getting the software, of course, you have to be able to run SAS today to do this. So getting the macro downloaded to your machine and the user's guide to look at it. And then if you've used SAS, but you have never run a macro in your life, that's no problem. We have a 3 or 4 minute video that you can watch on the same website. You can just click on it and watch how to run a SAS macro in general. And then it's quite easy. And then we'll walk you through it in the user's guide.
It sounds like that could be.
Something else I would recommend is to find an application that's been published that is most similar to what you want to do. And chances are, if it was written by someone in our center, the syntax is included as an appendix.
Good. Thank you. You could put that video on YouTube and see if it goes viral.
Oh yeah, SAS Macros.
You have another question from our audience.
Yeah. What about outcome measures that are highly correlated over time? How do they affect coefficients estimated via TVM?
Outcomes that are highly correlated over time. So, coming myself from a background in latent class analysis, I'm very keen on outcomes that are multidimensional, complex behavioral multidimensional outcomes. TVM, however, is linear regression. It is regression, and the effects are these, incredibly informative non-parametric functions of time, but it is still regression. And so the same limitations that you have in linear regression, you have here. The outcome in TVM can be a continuous variable. It can be binary. It can be a count. It can even, in some cases, be a zero inflated count outcome. But it is a single unidimensional outcome, and the other outcomes that you're interested in just don't come into play in the model at all.
You've used a couple of phrases that I want to make sure that I understand how they fit together. You've said several times that TVM is a straightforward extension of linear regression. You've also referred to it as non-parametric. And I don't think of those two things as going together. So could you help me there?
I'll try. So yes, if you think about linear regression, you're estimating a beta for the intercept and say a beta for the effect of X on Y. And that is what you get in regression. In TVM, that is also...
And you get parametric estimates.
It's parametric estimates.
Right.
And so you get, in TVM, you get a parametric estimate of X on Y in the intercept for a given time. So if you freeze time and you take one vertical slice from that figure, those figures that I've shown you, those are linear regression coefficients that are parametric. What's non-parametric is the shape of the function with age or time. And so the shape is basically the data let the shape of the function come to the surface for you. And there is, some selection going on behind the scenes or in a hands-on way to select the function, but the functions have no parametric function of time. And so whatever shape most accurately represents how those regression coefficients change across age or time are expressed in those figures. But within a slice of time or age, it is linear regression. Does that help?
It does. And how are you estimating those time-varying coefficients? Is that least squares? Is it maximum likelihood? How are you estimating?
They are maximum likelihood estimates, but the functions are estimated with spline regression. And so the TVM software has two different estimation options for the spline regression that's underlying TVM. One is called the truncated power spline basis function, and that's referred to as the P-spline. And the other is a B-spline basis function. And so the technical details of those two different estimation approaches that are basically under the hood of TVM are described in Chapter 10 of the user's guide. But so depending on which of those two estimation techniques that the user specifies, then the spline regression is operating behind the scenes and estimating the functions for those coefficient curves. And then there's I've alluded to a model selection procedure that it can be done either automated or manually to choose the exact coefficients that you're going to report in a manuscript.
Okay. From the two examples that you showed us, it's clear that you can handle repeated observations on the same people. So the software has to be able to take care of the correlation among observations taken on those same participants. You also showed us a cross-sectional example where we'd have no expectation for that kind of correlation. You had one question about correlated outcomes, but what about other kinds of correlation that often exist in data from prevention studies, from health-related intervention studies, where we may have a correlation among people who go to the same school or who live in the same community or work in the same factory?
Yeah, so these are great questions, David. And remember, these are early days of TVM, so more functionality will be coming in the next few years. However, I think where the software is at, we can answer a lot of our questions. So let's just kind of figure out where the software is today. So can TVM handle clustering within a person? Yes, as you said. And there are two different ways that TVM can handle clustering within an individual. That's repeated assessments within individuals over time. One way is through random effects, and that's in the B-spline estimation approach. You can have a random intercept, and if you want, perhaps a random slope in there. Alternatively, there's I would say the more user-friendly way, and when you're just starting out with TVM, I would recommend the P-spline approach. And that approach doesn't have random effects, but it uses robust standard errors, which is basically GEE. We have data very intensively assessed over time, and we want to think about mediation. Usually our mediator and our outcome are both assessed intensively over time. And how to model mediation conceptually is unclear in that framework to me today. But if you were simply wanting to know whether if you add this other predictor into the effects of these other predictors reduce, certainly you could do that today.
Okay, thank you.
There's a longitudinal element of mediation that I think is quite complex in this context.
All right. We apologize to our audience for the technical difficulties that we just experienced a few minutes ago. I don't know if others out in the audience had the same issues that we did, but I suspect that you lost picture and probably sound for a few minutes. And apologies for that. You have a question from the audience? Okay.
This person wanted to better understand how much space you can have between time points. For example, say I have 5 data collections over 20 years on n equals 1,000 of folks who are within 2 years of same age. If my time variable is age, I find that there might be 2 to 3 year gaps with no person time data point. Can you shed any light on this?
Well, we have not investigated to the full extent sort of what the exact data requirements would be in a situation like that. However, I will say when we first started to apply TVM, we thought that the data requirements would be quite intensive, that anything that you might fit a growth curve model to reasonably, which is like 5, 6, 7 time points per individual, that you would have no business using TVM. But I don't think that's quite the case. In the National Youth Tobacco Survey data that I showed in study 2, we had age coded to the nearest year only, and it was so we had individuals that were 11, 12, 13, and so on up to 19, and we were able to estimate quite interesting time-varying effects. I think as your data become more and more sparse and your time between ages becomes larger, I would say that what's likely to happen is not that TVM won't work, but you just won't pick up on any kind of complex functions. And so the parametric functions with time will probably tend to get quite smooth, in which case you might just be better off estimating a linear parameter for time.
Okay, I have another question. In your ESIG example, you had cross-sectional data, but your method gives the impression of longitudinal data from which one could distill causative effects. Your approach with the odds ratio seemed to give the impression that ESIG was a gateway to normal SIGs, but it could also be that normal SIGs are a gateway to ESIGs. How do you distinguish?
We would need to have certain kind of data in the survey about which came first for an individual, and we did not have that in the NYTS data set. I wish we did very much. I think that the fact that at many of these ages of adolescence from 11 to 19, the fact that many of them are using e-cigarettes more than they're using regular cigarettes is quite telling. And the fact that regular cigarettes are more problematic, at least in terms of cancer incidence. Thinking about e-cigarettes as a potential pathway to the more risky combustible cigarettes is of interest. However, it is, I should just say this more broadly too. If you're using TVM in your research and you want to talk about these time-varying effects, it can be more useful in the context, in the body of the paper, to refer to these as time-varying associations, so as to avoid this idea that there is a causal effect. These are regression coefficients and nothing more. And so they should be interpreted as such. And so the odds ratios, we could have fit the model in the opposite direction, but these are associations with age. There was another question embedded in there, Renelle, that was about using cross-sectional data, and it conveys this idea that we're looking at things developmentally or over time or age. And really, I think, the way that I think about those models is to keep it very clear that we're looking at a snapshot in 2014. This is very, very recent data on tobacco use, tobacco products. And at that snapshot of time in 2014, we have a huge, wonderful sample of adolescents, and they span these ages. And so we're really thinking about age as a very important descriptor in how the behavior manifests itself in the population today. And so it's important to keep that in mind, and that it is not a developmental study. The main reason why you would want to be, I think, cautious about thinking about that as developmental trends is because we know that over historical time, e-cigarette use is shifting very, very rapidly. And so there's no reason to think that those kids who are 11 in the survey in 2014 will look in 8 years like the 19-year-olds do in that survey. They'll probably look much, much riskier.
All right. Well, thank you so much, Dr. Lanza, for all of the useful information. And thank you to everyone who participated in today's webinar. On the Medicine Mind the Gap website,
Thank you so much.
which is again prevention.nih.gov/mind the gap, you will find several resources for this talk, including slides, references, experts, and a link to complete an evaluation. Your feedback is very important to us as we plan the remaining sessions for 2016. Thank you again for your time.
Thank you, Dr. Lanza.
Thank you. Thanks, David.